This microchip is capable of sending messages over 12 miles away without the need for any kind of cellular network. And that's just the beginning. Tiny, cheap, and unregulated, devices like these are making use of free long-range radio protocols like LoRa to send peer-to-peer comms in extreme environments never before believed to be possible. Advancements in outfitting this kind of tech on everyday hardware like Raspberry Pi, Arduino, or ESP32, or even hacker boards like the Flipper Zero represent a shift so profound it promises to redefine how we think about connectivity. Bold claim, I know, but I covered long-range mesh networks in my last video, and the response was absolutely explosive, which signals to me that this is truly an idea whose time has come. Since then, I've discovered even more powerful hardware and gained deeper insights into what makes this movement so significant. And given the disruptive nature of this technology, there is a high chance that this video might not be up for long because industry giants prefer you not see this. Tiny tech like this is going to change the smart device ecosystem forever, and after today, it'll never be the same. Let's explore exactly how it challenges the status quo and even discuss how it could one day possibly even save your life. This is the RYLR 998 by Rayax. It's a blue chip less than half an inch wide featuring an ultra long range LoRa modem. The PCB features an aesthetic dove-shaped cutout to signify that it also transmits vibes of peace and love, which is something we can all use more of right now. Unlike many comparable devices on the market, this chip boasts a low-profile antenna and doesn't require any extensions or third-party add-ons in order to function. Now, this chip serves as a transceiver, meaning it can both send and receive messages. And priced under $13 on Amazon, it's a bargain, especially considering the turnaround on getting this device delivered was lightning fast at 2 days. In addition to nabbing the RYLR 998, I'd suggest getting these accompanying USB to TTL 5-pin serial converters because they'll make it compatible with virtually any hardware that supports USB. And for this demonstration, this is all you're gonna need. After they do arrive, you'll end up with the RYLR chip itself, a few jumper cables, and the USB to TTL converter. Now, this thing is surprisingly versatile. It can be accessed over UART. Physically, it connects to devices over GPIO with 4 distinct pins. This means it can be used fairly easily with microcontrollers like Arduino, ESP32, and Raspberry Pi devices. But for those less versed in the ways of GPIO dark magic, you'll be able to use the USB to TTL converter, which is going to make it compatible with any standard USB, which means you can connect it to your phone or your computer just as easily. So let's walk through how it works. So first, we line up the jumper cables. Next, we can plug this in and we'll see a red LED lighting up indicating that the device has power. So again, this chip is only a peripheral. It still needs a compute module to run a program that will interface with the chip and issue commands. So for the purpose of this video, I'll execute the code directly on my computer. But you could export your program to a microcontroller like an Arduino or an ESP32. Okay, so when it comes to the hardware schematic on this thing, you have 5 pins on the RYLR device. You have VDD, which is the power supply, NRST, which is the reset. You have RXD, which is UART input, receive, or TXD, which is UART data output, and GND, which is ground. Now, really, instead of memorizing what connects to what, it's fairly intuitive in that ground connects to ground, power connects to power, but keep in mind the RYLR needs 3 volts, not the 5 volts. So VDD on the RYLR is going to connect to the 3 volt power on the USB. And then RXD, which is input, connects to the output on the other device. So don't get tripped up on that. So TXD goes to RXD on the other device. And then RST, reset, is not used in this case. As long as you follow that pattern for hooking it up to the TTL USB converter, an Arduino board, or another microcontroller, you should be all set. Okay, and then with our device connected, we're gonna open up Arduino IDE just to make sure it's available and we can talk to it. So what I'm gonna do is I'm just gonna do new sketch, kill this old one here, and then I'm gonna go to board. I'm going to go to select other board import. I'm not even going to select a board. I'm just going to select the new port that has been available as of plugging in the RYLR device. So let's just do OK. And let's just go ahead and open up a serial monitor. So we need to make sure that the baud rate is set to 115200. And then we also need the formatting of new line and carriage return. But if we just type anything in here, we're going to start to get messages back. So this is the RYLR sending, it's responding to the command and then it's sending back a message. There's a whole schedule about each error message. It doesn't even tell you what the error is. You have to look it up, but they are helpful. And we know it's working because it's always the same format here. And if we just want to query something real quick, like the address, we can just do AT plus address question mark, and it's saying, okay, the address is 2. And so everything seems to be working fine. Now we can do everything we want to do out of Arduino IDE, but I actually have been using another tool called Platform IO. And so it's compatible with VS Code. I use Cursor, which is a fork of VS Code that has Gen AI and Copilot built right into it. But what you can do is you can go over to extensions here, and then you would just download Platform IO. Let's see, it's right here. So you would just install it, and then you could restart VS Code, and it's going to give you a couple new options. So like what I do here is I just go to the home page. There's this whole section here, and then you can create different projects. The projects create their own configuration files, directories, Git files, and things like that. So I find it helpful. So I have this guy set up here for the RYLR 998. So what I could do is I could go ahead and open it, and it's going to put me over into the platform.ini file. What's nice about this is we can set the baud rate. We can set the port. If we don't know the port, we can go back over to home. We can go to devices, and it's going to give us everything it sees. And so we can see this port here. And if we unplug it, this will go away. So you can just copy this guy over. And then we can also give some parameters around how the serial terminal is going to work, and then the board and the framework and stuff like that. But to open up a serial terminal using Platform IO, you just come down to this guy here, and I think we're going to be good. Let's see. Yep. Okay, so our device is connected. We've specified the baud rate and also the message formatting, applying a new line and carriage return with each message. Now, when interfacing with the RYLR, we use what are called AT commands, and they're a set of simple API commands for data exchange and parameter configuration. With these devices, we need to know the device address in order to send messages, so we can query the device's assigned address by running AT plus address question mark. Similarly, we can set the address by running AT plus address equals 5, which will set the address to 5. If we run the command AT plus parameter question mark, this will give us the following parameters. Now, LoRa network configuration involves setting up essential parameters for device identification and communication. AT plus address assigns a unique address for identification within a network. AT plus network ID sets the network's ID to ensure group communication, and only devices with the same network ID can interact. AT plus band selects the communication frequency band, and all devices must match this frequency to communicate. AT plus parameter adjusts the RF parameters like spreading factor, bandwidth, coding rate, and preamble for synchronization and data transmission efficiency. AT plus send initiates data sending to a device with a specified address, considering transmission time and programming overhead. Tweaks in bandwidth and spreading factor balance throughput with distance, and bandwidth affects transmission speeds and sensitivity, while spreading factor influences signal reach and transmission rate. LoRa technology is designed for scenarios where only small amounts of data need to be transmitted intermittently, such as sending around 100 bytes every 10 to 15 minutes. This modest data rate might seem limited by today's standards. However, it is quite adequate for many IoT applications that don't require transmitting large files like images, audio, or video. Instead, LoRa excels in applications such as remote device control and sensor data collection, where the primary goals are minimizing power consumption and maximizing battery life. With its capability to control hundreds of devices simultaneously within these parameters, LoRa offers an effective solution for many modern IoT setups. So I'm going to turn on another one of these so we can send messages. So for my second node, I'm going to connect it to my Android phone. Then I'm going to download a serial USB UART application that will load a serial terminal for the RYLR device. Okay, and then I just want to show you real quick how you would set up one of these guys with Android. It's very straightforward. You can use the USB converter. The Android phone obviously is going to have USB-C, but this should take care of that. So let's go ahead, see if we can't get that going in here. Okay. Okay, so you can see that it's powered on. What I'm going to do is I downloaded an app called USB Serial. As long as it's plugged in, you should be able to connect. It says it's connected. If we send a message, yeah, so we get the error message. So it's really easy to get one of these going with like a computer, a phone, Arduino, ESP32, Raspberry Pi, RPi Pico, etc. So it's a very versatile device. So now we could issue all our commands. We could set the network bands, modify the parameters, and you can also send messages from here, right? So if I wanted to send a message, I could do AT plus send equals the address. So say I had another device at address 5, the number of characters in the message. So I could do 5, and then I could do hello. And that was sent out. From there, we can send and receive messages. So we've got comms, albeit small ones, but small is good when it comes to things like energy footprints. So let's see exactly how much power these things actually draw. So one thing to note is that these actually use a 3.6 volt, not a more standard 5 volt. So when I plug into this power monitor, we can see it's pulling 0.02 amperes, which if you do the math is about 0.07 watts, which is basically nothing. For reference, my iPhone will pull 5 to 25 watts at any given time. So this minimal power draw means it'll do great with lithium batteries or even green energy like solar. However, we got to talk about Meshtastic. So the question is, can it function compatibly with Meshtastic software? And the answer is no. In the realm of LoRa hardware, you're essentially dealing with two types of interfaces, UART and SPI. UART is straightforward and great for simple serial communication between devices like a Raspberry Pi and a LoRa module, using just 2 wires for data transmission. SPI, however, is faster, supports higher data transfer rates, and can connect multiple devices. The choice between UART and SPI will depend on your project's complexity and speed requirements. And Meshtastic only works with SPI radios. So it will work fine with this Heltec LoRa V32 board, but not with this WaveShare SX1262 LoRa hat. And unfortunately, it won't work with our RYLR device either. But that's fine because programming these things is not hard. So I'm gonna run a rudimentary range test to show what these things can do. So we have a limited set of commands, and what we're gonna wanna do is to write a script that sends a message from node A to node B every 5 seconds with an incrementing counter so we know which messages we're receiving and which we're dropping. It also needs to compute the size of the message and provide that result as an argument in the send command. But that's easy to do. Technically, you could write this script in pretty much any language, but I ended up going with Python. So I have this script here, and if I execute it, you can start to see it firing off messages. Then if I connect node 2, we can see the messages start to come in. So I'm going to situate the antenna from node 1 high up on this window, and I'm gonna run out on a peninsula where I live and see if we can't get some messages to go through. So what I did is I created a Python script that uses those AT commands, and it sends out a message every 5 seconds. So let me show that to you real quick. But again, you could use any programming language, shell, node, whatever. So it just, again, Python script, I import a module called serial. We specify the port. We specify a little function here, and basically what this function does is it creates a message where the prefix is MSG and the suffix is an incrementing counter. And as you can imagine, it can go from 1 to 10,000. So the size of the message is going to change. So you have a little line here that computes the size because that's going to be an argument in the AT command that we just ran down here, right? AT plus send equals address, message length, message, new line carriage return. And you're going to need that new line carriage return or else the response won't come back correctly. And then all we do is we loop, right?
every 5 seconds, increment the counter, send another command. So let's see if we can't get this working. Now we want to open a traditional terminal here. So what I'm going to do is, right, and when I say traditional terminal, I'm talking like a bash terminal, right? Now let's go into the source directory, and I do need to enable my Python environment. So let's see if I have that command. Okay, looks like I do. So what I should be able to do to run this script is just do Python rangetest.py. Okay, and it's running. So again, I just ran my Python script. It is looping every 5 seconds, and it's sending a message with an increment, 0, 1, 2, 3. And so if I had my other RYLR device set up, I'll be able to receive those messages. And what I'm going to do for the range test is just let this run. Right, so now I have the script running. And what I'm going to do is I'm going to take the second radio, and I'm going to bring it out to, let me show you where I'm going to go. If you can see way out there, there's like a peninsula several miles away, and that's where I'm going to run to and see if I can't get a message to come through.
Hold up one sec. If you're interested in how you can competently bring your ideas to life, whether it be through rearranging bits through software programming or rearranging atoms through creating your own hardware, I'd strongly suggest getting proactive about your education. And a great way to do that is through self-paced learning tools like Brilliant.org, the sponsor of this video. Brilliant is where you learn by actually doing, with thousands of interactive lessons in programming, AI, and other future-facing fields. And inside Brilliant, you'll find content crafted by an award-winning team of teachers, researchers, and professionals from the likes of MIT, Microsoft, Google, and more. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/dataslayer by clicking on the link in the description below. They'll also throw in a 20% discount on any annual premium subscription. Thanks.
So something that was interesting was as we were leaving my apartment to run the range test, we were still receiving messages about 10 floors beneath my apartment in the parking garage as we were driving out. Now, presumably each floor has, a fair amount of concrete separating the other floors. So it was just interesting because it contradicts the idea that you need a perfect line of sight in order for these things to work. Granted, they were within close proximity, within, in the order of hundreds of feet, but still it was penetrating that dense material and successfully sending messages. Okay, so once we got out to the peninsula, I was pleasantly surprised to find that we were receiving messages, and this was at over 3 miles away. Now keep in mind there was a good line of sight right over the water, no obstructions. I was not able to test any further distances, but if we wanted to try to extend that range even further, what we could do is mess with the band settings and optimize for distance while reducing the throughput. And that would be one way we could probably get more range from our devices, but I was fairly impressed with what these were able to do. 3 miles with these tiny profiles is quite good.
So I went for a run and the test worked. As I was out on a bridge with a good line of sight, I started to get some messages, proving to me the power of these tiny LoRa radios. Now, while I was working with these LoRa devices, an idea struck me. Could this technology enhance safety for extreme hikers like my friend and I? For years now, my best friend and I have been avid winter hikers in New England. We've taken up to the White Mountains and Appalachian Range that span Massachusetts all the way to Vermont. Our foe, Mount Washington, situated in Gorham, New Hampshire, is particularly risky when it comes to winter hiking. At under 7,000 feet of elevation gain, it's hardly the most prominent peak in the US, but located at the mouth of a common jet stream, it gets insane weather. The wind funnels through, and I've heard it described as a similar phenomenon to when you place your thumb over a hose and the water pressure picks up exponentially, which is why Mount Washington boasts the second highest wind speeds on Earth. Now, we love hiking up there, but often we're going out in 70-mile-per-hour winds, temps 20 and below, and visibility dropping to whiteout conditions. Imagine having to navigate 10 miles without being able to see 50 feet in front of you. Now, we take great caution to be safe during these adventures, but nothing is guaranteed. And seeing as how LoRa does well with open lines of sight, and particularly in elevated areas like on mountains, I wonder how it might be used under these conditions to keep my friends safe. One possibility could be to put a weather station at the top that transmits down essential information like temperature, humidity, and wind speeds. This would help hikers make better decisions in the moments leading to their decision of whether to go for it or not. For other scenarios like emergency SOS via satellite phone or GPS coordinates, Garmin probably has better alternatives. And although LoRa might be a good candidate for disparate groups to communicate, we usually don't split up because that's just a bad idea in general. Anyways, I find it promising that I could potentially build something with this new tech to help keep my friends safe. When it comes to my own Tinker projects, LoRa communication is definitely something that I'll be adding to my arsenal. It's tech that I believe will stand the test of time, government bodies permitting. Anyways, to go further down the rabbit hole, check out this next video.